My pleasure, and I'm thankful to MX Business team and the entire committee to invite me for this talk. I'm an academician and probably the only one here, whomever I have met so far. So my talk will not be really in the same domain or similar domain what you have been seeing so far. I have tried to keep number of equations and number of variables in the, like all the constants and all the Greek letters as minimum as possible, and I've tried to keep as many pictures so that I don't push you into slumber. So here I'm going to talk about one particular system. There was some brief discussion on this system in yesterday's panel discussion. So if you remember, when we were talking about steel construction, we were talking about what system would we use for the core design, for the design of the core, which basically resists most of the lateral load. And there was some discussion on going for regular RC versus composite construction for that. So this is something that has been investigated in quite a bit of detail in the US, and some Japanese investigators, researchers primarily, they had investigated back in the 80s also. So this is not something very, very new, but suddenly it has picked up some steam now, primarily because of the pace of construction has become a very critical issue again, and that's why some of these new projects in the US that are using this technology. So that's what I'm going to talk about. So why do we need a core in any structure? We can always resist lateral load coming onto a building in various ways. We can use a braced frame system, we can use a moment resisting frame system, but all these systems have been found to have a lot of limitations. So braced frame systems inhibit our ability to put windows and doors, for example. So if you want to put windows and doors in a building, braced frame systems are not really very ideal system. Moment resisting frame systems are very flexible. If you want to make it really, really rigid for a tall building, you have to make beams which are deeper than the floor itself, right? So then they have a limitation. Therefore, typically whenever we go beyond a certain number of stories, maybe 12, 13, always we would go for a core, a rigid core, and then there would be some kind of a gravity load system around it. So what you see in this image here is at the center, what you see is basically a core. This core could be made of various systems. Typically, it is an RC kind of a shear wall core, and around it you have the gravity load bearing system. So these we call as leaning columns. They don't resist the lateral load. They simply sway as the core sways, and core is the one that offers most of the rigidity. And most of the diaphragm action makes sure that what we call is a floor slab or diaphragm, which ensures that the floor is moving by the same amount. So it's not like the core is staying in place and the rest of the floor is deviating more. So as long as we make sure this system works beautifully, right? So typically that's how the construction looks like, what you see on the right-hand side. Now, what is the challenge with the existing technology? As of now, we are using RC construction, right? So core is typically RC, reinforced concrete. But what happens when we go to a high seismic zone? With the revision of IS 1893 Part 1, all our seismic coefficients are going to get increased. We have to see, somebody has to solve the examples and see what is the new requirement for reinforcement with the revised IS 1893. But if the reinforcement keeps increasing, you can imagine the situation what we'll face in our shear walls. So you have to push concrete through this maze of reinforcement. And what you can't see probably very clearly in this image is also there are a number of reinforcement bars going diagonally through the beam link. So there are two shear walls and there is a beam in the middle, and there are diagonal members also going through that beam link. Imagine the complications that arise because of this kind of reinforcement running in all possible directions, and how you push concrete through it, what kind of concrete quality you can ascertain in such kind of a situation. Okay. On top of that, the codes say that you design this, you put this much of steel, make sure that steel fails before concrete does. So we put so much of steel, and then concrete has to be stronger than steel, so that steel fails, concrete does not, right? So all these are very challenging tasks. I mean, code committees do tend to give us very conservative guidelines, but then when we actually have to implement it, we somehow realize that it is not as easy. So designing of these link beams that you see in the middle is a very, very challenging task, putting those diagonal reinforcement. So, of course, there is a lot of labor involved, there are a lot of uncertainties involved, number of tasks that you have to accomplish before you build a wall like that. Form work, reinforcement, bending, placing, pouring concrete, all those tasks. Every task brings some level of uncertainty in the process. So all those things, why can't we find a way around it and reduce the number of uncertainties? So, plus another one is that if we have to do penetration through this shear wall for electric lines, etc., that's also a major challenge in the middle of all this reinforcement. So one system that actually, originally this system was used by the nuclear industry and primarily by Japanese nuclear engineers. So they have to build very heavy, bulky systems for heavy earthquake conditions. So they went for this kind of a sandwiched panel walls, which was meant for nuclear safety structures. So this these walls basically consist of 3 primary components. There are 2 face plates, which work as reinforcement at the end, but initially they basically work as formwork. Then there is concrete infill, and just to hold the 2 face plates together, there are shear ties. So that is a very simple, elegant system, and that's what they had come up with. The idea is that the erection of the steel plates precedes the concreting. So you can go 1 or 2 or 3 stories ahead of concreting. So concreting can take its time, but you can keep erecting the steel plates quickly so that you can develop a kind of a support system also to which you can connect rest of the frame. You don't have to really wait for concrete to cure. Okay. And there are certain advantages with respect to using pure steel also. I'm not going to talk about too much on that. I'm primarily comparing with concrete. What are the advantages here? So there are 3 components. Of course, concrete has major load-bearing role that nobody has any doubts about. In addition to concrete, there are steel plates, which we call face plates, and there are shear connectors, right? So what is the purpose of steel plate? Quite obvious. First, initially, it works as a formwork, right? During the erection process, it carries the self-weight of all the stories that you have built above it, even before concreting, right? So that itself, it carries the self-weight. Also, it resists the construction load. So any additional load that might come because of construction, that it resists. After the curing is done, after concreting is completed and curing is done, then it simply behaves as a reinforcement. So it is only sitting on the outside of your wall and behaving as reinforcement, tension reinforcement, shear reinforcement, name it. Okay? Then there are ties, cross ties you may call it. So cross ties could be provided in 3 primary configurations. There can be cross ties which are connecting the 2 face plates all the way through the thickness of the wall. That is the first, the middle picture here. Also, the cross ties could be provided in a way so that they only transfer the force between concrete and steel, but do not tie the 2 steel plates together. In certain conditions, that might be acceptable, where we can just call them shear studs or headed studs. So they are embedded into concrete, but not connecting the other side of the plate. Depending on the spacing between the plates and depending on how much loads are getting transferred to the plates, we may sometimes have to provide diagonal ties also in certain conditions to ensure stability. So all these have to be designed, and of course it can be designed. They have been designed. There are design guidelines available. So if we design all these components carefully, we can make this kind of a system work easily. Okay? So the purpose of the ties is basically to, while handling, while shipping, while fabrication, to make the geometry intact so that it does not buckle, it does not bend, the plate system stays in place. During the erection process, whatever the loads are coming, because of wind loads or because of erection loads, self-weight of the wall itself, it should not fail. You might have all heard of the incident in Bangalore metro construction, where a reinforcement cage had collapsed, right? So such kind of things should not happen. So the ties serve a purpose there. Okay. Then during the pouring of concrete, the wet concrete will apply hydrostatic pressure on the plates. It will push the plates away, and these ties can help hold the plates in and reduce the deformation of the plates under hydrostatic pressure. That could be another application, another use of these plates. So all these will be governing the design of these shear ties, and there are provisions for that. So subsequently, when the axial loads are applied on this wall, at that time, axial load could come from gravity load, or it could also come from earthquake load, wind load, etc., which will be flexure primarily, but a component of that will be in compression. At that time, concrete, when it goes into compression, it requires confinement to be effectively utilized. So these ties can provide you that confinement also. Okay? And then eventually, when there is flexure required, and the plates, the face plates are going into tension, etc., they have to be tied with concrete so that force transfer can take place, and the whole system can work in composite action. For that, they help with transferring of the force between concrete and steel. What are the major advantages of this kind of a system? Of course, it is a faster construction. Now that can be, we can add a caveat: if you don't have the manufacturing capability to manufacture or to fabricate these plates, then of course it is not a faster construction. So as long as there is no logistical bottleneck, it's a faster construction, because we don't have to wait for concrete to cure, for the core to get ready to start taking the load. Okay? Precisions are better in comparison to regular RC. So wall surfaces are very clean, flat surfaces you will get. Reduced wall thickness, because you are using much more amount of steel, wall thickness can be reduced. Concrete quality improves because we are going to go with honeycomb, we are going to go with self-compacting concrete, and there is not so much of reinforcement bar, so many reinforcement bars inside. So self-compacting concrete, we can pour it from much higher levels, and still we can maintain a very good quality concreting without any vibrations requirement. Steel, a lot of steel is being used, so there is natural ductility available to us. We can prevent buckling, so if the buckling is prevented, shear failure of the connectors is prevented, we can be guaranteed of very good ductile behavior from these wall systems. There are a couple of pitfalls. If we avoid that, we can get a very ductile behavior. Very stiff system, just like RC walls, even more stiff than RC walls. Modular design, that means we can bring in components to the site and erect rather than doing all the cast institute testing. And then some guidelines are available. So before I go into the design provisions and talk about some design considerations, I will talk about these two case studies. The good thing is that there must be more buildings which are built using this technology, but these two are nicely documented, so that helps us. So this is a building that was built in Seattle. The construction completed in 2020. Took about 3 years from the foundation all the way to the top to complete. 58-story building. It's known as Rainier Square Tower. The designers claim, the builders claim, that they saved about 10 months' time if they had gone for, in comparison to the case where they had gone for RC. So they did an estimation. They found that there will be 10 months of saving if they had, out of 32 months, basically. So that was a major advantage for them. And a lot of cross ties were used. This was the first building, at least, which was documented like this, which was done with scientific input. So they were extra conservative. They put a little bit extra number of ties, etc. So about 2.5 lakh ties were used. They applied fire protection also, even though it was not really required. They ordered special steel because their floor heights were 14 feet, and they did not want to splice the plate within its floor height. So they ordered special steel from Korea, which was 14 feet wide. So that steel was used. So some such challenges would be faced whenever you go for such a project also. So their story height was 14 feet, so they went for that kind of a steel. Okay. They also found that fabrication was the bottleneck. So even though they were expecting the speed to be much faster, it was not as fast because fabrication was getting delayed. Now, of course, they could have expedited that further. Moving forward to the, so this is a picture of that shear wall that they had used. Moving forward to the other building, which is built with the lessons from the first building. And in this particular building, they had only 19-story building. There, they were able to really optimize the design. So instead of 12-inch center-to-center spacing, they went for 18-inch center-to-center spacing. They used a combination of RC shear walls and composite shear wall so that they could expedite the construction process. So basically, they took a lot of learnings. They did not use any fire protection because by that time, a lot of research had come out which had shown that there is not much of fire protection required. This is the typical construction sequence that they followed. This is the mat foundation. In the mat foundation, they had used these members which were embedded into mat foundation. These members are not composite. They are pure steel. And on top of that, what you see is actually the composite wall. So it's basically a hybrid of composite and steel. So initially, under that, there's steel. Now, those steel members are going to be embedded into shear walls. So you can see the bottom part of it is pure RC shear wall. Then grade level onwards, it turns into composite wall. And then composite wall keeps going one floor after another. And you can see as it comes to the grade level, then they start erecting the frame also around the core. This is how the core can be connected to the other framing structure. So the connections are pretty simple. Most of them are welded joints. You can do some level of testing has to be done, but then it can be very easily connected with the remaining structure. There are some guidelines which have been developed. These are not codal provisions. These are design guides. Right? So they are not enforceable, but still one can use for designing as long as your authorities, local authorities are willing to accept them. So there are some considerations regarding what is the minimum amount of reinforcement. So they have come up with different levels of minimum and maximum amount of reinforcement, that is cross-section area of the plate, for example, in comparison to the total cross-section area of the wall. There are some requirements, how much thick the wall can be, how thin the wall can be, likewise. So most of these are basically governed by whatever test data was or research data was available. In addition to that, it was also governed by certain types of failures, because while erecting, there should not be some kind of failure and so on. So all those things they considered, came up with these limits. Also then there were limits on how thin the wall could be, the plate could be. So for a given wall size, how thin the plate could be, or how far spaced the shear connectors could be. So there is a provision which is basically plotting your strain value versus normalized strain versus normalized slenderness value. So basically what it turns out to be that if you ensure that your slenderness, that is 1, if it is below 1, it should be less than 1. If you are in this range, generally you are safe. What this provision is trying to accomplish is that my face plate should not buckle before it yields, because buckling is more of a brittle type of a failure. We don't like buckling. We are okay with yielding. So it is kind of trying to enforce that we should have yielding-driven failure. Also, there are requirements on how closely the shear ties have to be available or presented. So there are, again, based on the development length, very similar to our development length concept from RC. And also it is based on the shear failure of the system. So the system should fail in shear throughout the cross-section rather than failing at the interface. Then there are other design considerations. I'm not going to go into each of these provisions. There are tensile design. So people have done a lot of research in this area. There are provisions available for blast resistance, for fire resistance. Please feel free, if you are considering some such system, go to these design guidelines that I have mentioned. If you have any further questions, we can have this discussion of the, like offline sometime. And please let me know if you're interested in this kind of work further. Yeah.